In this video we study the fundamental problem of keeping clocks synchronized in a distributed system. This is an important topic because computational devices must ensure a certain level of synchronization in most systems. Rather than focusing on any specific type of device, we simply use the abstract term node to refer to any device that is part of a larger distributed system. Nodes can coordinate with other nodes by exchanging messages over some communication channel. We assume that each node is equipped with a clock. As time passes, the clock value increases. We use integer numbers here to indicate the clock value, which is some representation of current time. As we can see here, the real time that passes between increments of the clock value is not guaranteed to be the same. These deviations occur because clocks have a limited precision, which affects their accuracy over time. In other words, the rate at which the clock value changes is itself a function of time. We assume that there is some small parameter epsilon such that the clock rate is always between 1 minus epsilon and 1 plus epsilon. Here we see the clock events at two different nodes, V and W. It is easy to see that node W is somewhat lagging behind. The difference between the clock values of two nodes is called clock skew. How could we reduce the clock skew between the two nodes? The only way for W to learn about the clock skew is for node V to send node W a message containing information about its current time. Obviously, it's not so simple because some real time may pass until the message arrives at node W. We assume that there is some constant t such that all messages arrive at the latest after t time. In our model, messages are allowed to arrive instantaneously, but of course they cannot arrive before they are sent. So, all message delays are in the range from 0 to t. Note that in a network where message delays are largely predictable, the range from 0 to t can be understood as the unpredictable part of the message latency. Given this uncertainty regarding message delays, how well can we synchronize clocks? Let's consider the following scenario. The clock rate of nodes V and W are 1, that is, they advance exactly at the rate of real time. However, the clock of node V is half of t ahead. If node W receives a message containing V's time after a delay of t, node W sees that its current clock value is actually ahead by half of t. Similarly, if node V receives a message from node W without any delay, node V sees that its clock is ahead by half of t. Both nodes make the same observation, and so neither node knows which node, if any, is ahead. Intuitively, a clock skew of half of t cannot be prevented between neighboring nodes, that is, between nodes that can communicate directly. It can be shown that this is indeed the case. No algorithm can prevent a clock skew of half of t times the diameter of the network, which is the longest, shortest path between any two nodes in the distributed system. We can even prove a stronger lower bound under the following assumption. We said that the clock rates are always in the range 1 minus epsilon to 1 plus epsilon. The best we can hope for is that the clock values are always at least 1 minus epsilon times the elapsed time and always at most 1 plus epsilon times the elapsed time. Let's now prove a lower bound under the assumption that a clock synchronization algorithm must not violate this condition. We consider executions of any clock synchronization algorithm for specific durations. We consider a path of length d from node V0 to node Vd, where V0 and Vd are some nodes at distance d. Capital D here denotes the diameter of the network. We will now construct three different indistinguishable executions for our proof. In the first execution, all clock rates are always 1 minus epsilon. Messages to nodes closer to node V0 are delayed by t, and messages to nodes closer to node Vd arrive instantaneously. We consider this execution for a duration of dt divided by 2 epsilon. In the second execution, all clock rates are 1 plus epsilon. All message delays are adjusted so that the messages are sent and received at the same times based on the node's local clocks. For messages to nodes closer to node V0, this means that message delays are now 1 minus epsilon divided by 1 plus epsilon times t. For messages in the other direction, the message delays remain 0. Since all events occur locally at the same times, execution 1 and 2 are indistinguishable. Note that we consider execution 2 for a duration that is d times t divided by 1 plus epsilon shorter. It is important to see that the nodes are not allowed to change their clock values, neither up nor down. If a node decreases its clock value, then it violates the condition that the clock value must be at least 1 minus epsilon times the elapsed time if the nodes are in execution 1. On the other hand, if a node increases its clock value, then it violates the condition that the clock value can be at most 1 plus epsilon times the elapsed time if the nodes are in execution 2. Let's now look at the third execution, where the clock of node V0 runs faster than the clock of node V1 and so on. The clock rates increase by 2 epsilon divided by d from node to node. We get that the clock rate of node Vd is 1 minus epsilon, and the clock rate of node V0 is 1 plus epsilon. What does that mean for the delta between neighboring nodes? And what are the message delays? The delta is at most the maximum duration times the difference in the clock rates, which is t. Since the clocks of nodes further away from node V0 run more slowly, message delays increase. However, since the delay was 0 before and increases by at most t, the delay is at most t. Similarly, messages in the other direction must arrive at most t time earlier, which is okay because the delay in execution 1 is t. So, we conclude that it is a valid execution, indistinguishable from the other two executions. Let's analyze the worst-case clock skew. As we saw before, it takes dt divided by 1 plus epsilon, more time for node Vd to reach the same clock value as it has at the end of execution 1. Since the clock rate of node Vd is 1 minus epsilon, the clock skew between V0 and Vd when V0 reaches the end of the considered time period is at least 1 minus 2 epsilon times dt. It remains to answer the question how close to this bound we can get. As we will see, a simple algorithm already gets us very close. Let's describe the algorithm by examining the actions of some node V. Node V has some neighbors, that is, nodes that it can exchange messages with directly. Whenever V's clock value reaches the next integer number, it prepares messages containing this clock value for all neighboring nodes. It then sends the clock value to these nodes. Of course, node V also receives such messages from other nodes. When it receives a message, it checks whether the received clock value is greater than its own clock value. If this is the case, it sets its clock value to the received clock value. Since the clock value must be a larger integer, node V then informs its neighbors about its current clock value. This is already the entire algorithm. Let's analyze how large the clock skew can get. We compare node V to a virtual node, which is always the node with the largest clock value. So this virtual node can magically change its identity over time. Let's say that the maximum clock skew is reached when the virtual node has clock value Cmax, and node V has clock value Cv. Let Cmax prime denote the last clock value that node V received from the node with the largest clock value. It is clear that it takes at most dt time before node V learns about Cmax prime. Some time delta may pass between the arrival of this message and when its clock value reaches Cv. Let's now reason about the relation between these clock values. Since nodes always set their clocks to received values when they're larger, it follows that Cv is at least Cmax prime plus 1 minus epsilon times delta, which is the minimum increase during delta time. On the other hand, Cmax is at most Cmax prime plus the maximum clock rate multiplied by the time that passes between Cmax prime and Cmax. Note that the node with the largest clock value never receives a larger clock value from a neighbor, so it can only increase its clock value at the rate of 1 plus epsilon. How large can delta be? Delta is at most 1 divided by 1 minus epsilon, as otherwise there must be a larger clock value than Cmax prime that arrives at node V at the latest at the time when its clock value reaches Cv. When combining these inequalities, we get that the clock skew cannot be more than 1 plus epsilon times dt plus some term that only depends on epsilon. Let's summarize what we've learned. We introduced the clock synchronization problem where the goal is to minimize the clock skew between the nodes of the system. We then showed that the worst-case clock skew grows with the network diameter and that we cannot prevent a skew of roughly d times t. Lastly, we showed that a simple algorithm guarantees that the clock skew between any two nodes cannot exceed d times t by much. Thanks for watching.